So we are today we will start the devices part of the course, and the first very important device that's the PN junction. So let us talk about the junction. So a PN junction is actually a single crystal. It's a single crystal grown such that one part is doped as P-type and abruptly the P-type doping is stopped and the N-type doping starts while growing a single crystal. It's not like you fuse P-type material and N-type material together and that will become a PN junction. That will not be a PN junction because that will not be a single crystal. So you cannot join two P-type and N-type crystals with each other and that will not be a PN junction. Right? So if I draw schematically a PN junction, right, it will be something like, if I call this as a junction, if this is a P-type material and this is N-type, suppose, right? So here the majority carriers are electrons, and here I will write this with plus, but it does not mean, right? It's not a positron. Usually this is represented. This represents a positron, but I mean holes by the positives. You know what I'm saying? It's not a positron. So concentration here of holes, of electrons, and here of holes. And the boundary which separates the two sides, that's called a metallurgical junction. This is called metallurgical junction. Now, because of the difference in concentration of these carriers, right, there are, we will say, electrons loosely bound to the nuclei, to the atoms, and here we say holes will be loosely bound. So, at normal room temperature, they will be almost all ionized.
Yes, sir.
Right?
Yes, sir.
So they will be able to move because of the concentration gradient. There will be diffusion force.
Yes.
Right? Diffusion force on the majority carriers. The majority carriers electrons, so they will move toward this side. Similarly, there will be diffusion force on holes to move from here to this side because of the concentration gradient. So electrons will move to this side, they will be occupied by the first available side for electron, that's the hole. So this side will become negatively charged. because of these electrons coming and sitting on the hole side, this side is neutral. It just does not mean that this is negatively charged. That's neutral side. They are neutral in charge. Neutral. They are not negatively charged. Similarly, these are neutrals. They are not charged. So, when electrons move, they will move from the nearest side. So, suppose electrons move from here to here. So, this side will become negative charge and they will leave a positive charge behind. When electrons leave an atom, it becomes a positive ion. So, here as a result, charges will develop, right? The region will become charged. Depends upon the concentration of your free charge carriers, what should be the width of this region. This region where there are no free carriers here. The electrons are sitting on the sides, tightly bound where there are holes, completing the bonds. So this region, this is called the space charge region. Space charge region. Or this is also called depletion region. Depletion region. Because they are depleted of the free charge carrier. Free charge carrier निष्ठा so depletion region free charge So these are some features, characteristics, structural characteristics of a PN junction. And when the doping of one type of material, of one type of impurities is immediately stopped and another starts. This type of junction is also called step junction. Right? When one type of carriers stops and another starts, this kind of junction is called step junction. Step junction. Right? Now, there is diffusion force on majority carriers which are electrons to move to this side. But as the electron move to this side, they ionize this side becomes negative. So now there is an electric force on the electron in this direction. So the concentration gradient which produces diffusion force, that diffusion force is balanced by the electric force and stops further moving of the majority carriers. There is a force on this electrons. These are electrons. That force will be the diffusion force. This force is the diffusion force to move electrons from the right toward the left. But because of this, there is an electric field in this direction, right? there is an electric field, and electrons will face a force opposite in the direction of the electric. So there will be electric force on the electrons side in this direction. Because of this space charge region, a force will act on the free electrons here to stop further flow of majority carriers to this side, of electrons to this side, to stop further flow of electrons. So the electric force balances the diffusion force. And this situation is called thermal equilibrium. Like thermal equilibrium is produced, is reached. Thermal equilibrium is when the Fg is equal to Fa. The diffusion force on the carriers is equal to
Electric force.
right? Okay. Now, if we want to write the situation in the energy, in the form of the energy band diagram, right? If that is energy, right, and take is suppose the metallurgical junction, right? We call this, this electric field can be considered as gradient of potential.
Yes.
We know that electric field can be represented as gradient of potential. So we say a potential difference exists across the junction. Potential difference exists across the junction. And this potential difference is called built-in potential, because no potential is applied from some external source. So it is a built-in potential of the PN junction. Right? That is called a built-in potential. The field produces a built-in potential. Built-in potential VBI, we will call it VBI, across the junction. Right?
Yes, sir.
Look, we say suppose this is the conduction band and this is the valence band, the band structure of the N type. So we say that the intrinsic Fermi level will be somewhere in the middle.
Yes.
Intrinsic Fermi level is middle.
Yes,
You know?
yes,
This will be the EFI, the intrinsic Fermi level.
Yes, sir.
And since this has been doped as N type, so from our previous knowledge, we know that the Fermi level moves with doping. So it will be close to the conduction band, that's the Fermi levels.
Yes, sir. Some of material dependent.
So same.
And
This is N-type material, so the doping causes the Fermi level to move up for electrons closer to the conduction band. The Fermi level moves with doping, right?
Yes, sir.
Okay, so it is like this. Now, if there is like during the growth, we have to see, if this is a separate situation, if I put it like this, no look, since this is an equilibrium, I will say, we say this is in thermal equilibrium, the Fermi level across the junction should be the same. Because if there is a Fermi difference in Fermi level, the charges will move from higher energy to lower energy. So since there is a thermal equilibrium, so we will say the Fermi level is the same across the junction. So this is the Fermi level. That is N type. So this is EF, the Fermi level. Right? Now, in holes, in p-type, the Fermi level is actually close to the valence band.
Yes, sir.
It moves closer to the valence band. When you are doping in p-type, the Fermi level moves closer to the conduction band. So the valence band. So the valence band should be somewhere here, closer to and the intrinsic level would be somewhere here, EFI बदल करेंगे. Our conduction band with the valence band है, because in p-type material the Fermi level is closer to the valence band. This and this is EFI, and this is the conduction band. So it's actually the band. There is a band bending now. Those with the conduction bands are मिला हुआ. और valence band the valence bands are मिला हुआ. So this band bending और the intrinsic Fermi level होगा से bend. सिर्फ Fermi level बंद बैठ की.
Yes, sir.
So this band bending represents the built-in potential. Right? Look, the electron energy is here now.
Yes, sir.
And when it has to move to this side, it has to go up
Yes, sir.
a barrier.
Yes, sir.
It has to go up a barrier.
Yes, sir.
That is the potential barrier. It has to face a resistive force because of the electric field, this electric field, which is in this direction. The force is in this direction. So there will be a decrease in energy of it, right? This difference, this is the right?
Yes, sir.
That energy is EVBI. VBI is the built-in potential multiplied by E makes it energy.
Yes. Yes, sir.
This energy is the built-in energy,
Yes.
built-in potential energy,
Yes, sir.
right?
Yes, sir.
This is energy. This is the same energy that we get from here.
Yes.
I'm just showing this an energy band diagram.
Sir.
This is called band bending, right?
Yes, sir.
This can be represented, this energy, this potential difference. With this energy is associated this potential difference
Yes, sir.
across the junction. This can be written in terms of a summation of this and this. The two the difference in the two Fermi energies. One this and one
Yes.
this. When we add these two, they equal to this energy.
Yes, sir.
Right?
Yes.
There's a difference in the two Fermi energies. If I call this, maybe I can call it a Fermi potential. So this energy is E F sorry, phi n. I will call it phi n
Yes.
on the n side. And this I will call this potential is
E
phi p, and the energy is E phi p.
Yes, sir.
This shows the difference in energy between the two Fermi levels.
Yes.
Here is the same. The difference in energy between the two Fermi levels, the intrinsic Fermi level and the
Extrinsic.
final load. So I can write that now this is the situation where we call it equilibrium. We call this
Equilibrium.
right? This energy, E VBI in this equilibrium, this can be written as the sum of the two energies. This one, E phi n plus E phi p. This energy is equal to this energy plus,
Yes.
right?
Yes.
That is equation number 1. Or if I divide it by equation 1 is what? If I divide it by what? By E, then that will be pi n plus pi p, and this is equation number 1. The built-in potential in terms of this potential and
This potential.
now we are going to determine what these potentials are. Now we want to know what is phi n and what is phi p. Okay, we know that in equilibrium and not dalunga, we know this. It is equal to e to the power minus ec minus ef over
Yes, sir.
kt, right?
Yes.
That is suppose equation number 2, right? Also, we know Ni is equal to Nc e to the power minus, right? Ec minus EFI by KT. When the intrinsic situation is intrinsic, right? So putting this here, look, this is NC, and this is also NC. Dr. Nasiruka, EFI 8 ko subtract. When we add subtract EFI here, this is kemunga dashera osteshwe, and this can be written as n not equal to Ni, right? And e to the power EF minus EFI or KT. And suppose this is equation 2, so this is equation number. So we wrote the free electrons in terms of the intrinsic free electrons. Now we define this potential as I said, that is equal to the difference between two Fermi energies. So define what? E phi n is equal to EFI EF minus E, right? FR. Let us define this as like this. So that is equation number 4. So 4 and 3 gives, right, and not equal to ni, right, e to the power minus e phi n over h. This is what we call this is minus e phi n. Now suppose we say at this temperature there is complete ionization. Complete ionization. So at complete ionization, right, we said that N naught will be equal to the number of dopants. So the dopants they are told ionized stability.
Yes, sir. Yes.
Very good.
Sir.
So putting this this is equation number. Suppose this is equation number 5. So putting this here and taking log at the same time.
Yes.
Putting this in this and take log. Take log. Right? So what we say log of ND will be equal to log of NI, right, minus E phi N over KT. The diagram. Okay. Log of ND equal to log of NI minus E phi N over KT. And our purpose is to pull out E phi N from here. So phi N from here, right? Phi N is equal to minus KT by E and log of ND over NI. Let that is the question number. So we got phi N. This side.
Yes, sir.
In terms of the doping concentration, which we know. This is doping concentration. We know this, right? And see. So similarly, we want to find the this one, this potential. So with similar procedure, right? With similar procedure, we find phi P equal to, that is H by E, and log of, and instead of ND it is NA by NI. This is NI, right? So only change is NA and NG. Right? And here is the minus sign, difference of minus. So that is question number 7. Right? So put this 7 and 6 in question number 1. One open yes. So 6 and 7 in 1. So VBI, we built N potential, that will be equal to KT by E, right, log of NA and D and divided by Ni squared. If this is equal to VT, I call it VT, thermal voltage. KT that's the boundary marker. KT is equal to 25 MeV. The energy, the normal thermal energy.
Milli-electron volt.
Milli-electron volt. Right? No electrons are खत्म शो. With the thermal potential we get.
Yes, sir.
Okay? KT by E. So E is खत्म शो. That we have thermal potential. So if we call it Vt, then it is equal to log of N Ni square. So the Belton potential in terms of what? In terms of NAND, in terms of the two dopants, in terms of the two dopants. That is how we determine the built-in potential of a certain PN junction made of a certain material with certain doping. Hey, that's what I'm going to take the first one.
Surgical bending to auto. The dinner depletion region is at home meet the down point.
We will do it. Right? In the next coming, maybe today or maybe tomorrow, we will find that. Okay, example. Consider a PN junction, right? T is equal to 300. Okay. And Na, the whole doping, p-type doping is 10 to the power 17 per centimeter cube. And Ng is equal to 10 to the power 15 per centimeter cube. And I equal to the intrinsic area concentration 10 to the power 10 and per centimeter cube. Right? So find VBI. What is the built-in potential in this situation? A PN junction of this type. Right?
Yes.
So VBI, we know VBI is equal to V thermal and log of Na and D divided by Ni square. Right? V, that is 25 MeV. E will cancel, that will be 25 and 10 to the power minus 3. Right? And volt log of Na and N D 2 to the power 2 and 10 to the power 15 17 over 3 10 to the power 15 divided by 1.5 and 10 to the power 10 whole square. Right? That comes out to be this multiplied by this, and that will be log of, right, 2 over 1.5 and 10 to the power 12. And that is equal to 0.0259 and 28. And that is equal to 0.72 volt. So the built-in potential of a PN junction with these characteristics will be equal to 0.72 volts. Now we can find the electric field of the across the p-n junction. Electric field in the space charge unit. Electric field in the space charge region. We have the space charge region, which we call the depletion layer, right? So what is the electric field? That's the junction. That's the junction. This is RP. This is N side, here, P side, P side, right? That's N side, that is P side. So if I write the electron density, the electrons in holes density, that's a constant here because it's a crystal, uniform crystal, right? So it will have the same concentration and the same density. So here, there is a positive charge, right? So if I represent this by rho, the charge density by rho, coulomb per centimeter cube. So there is a constant from here to here and drops to zero. And when the space charge region finishes, the density is 0. Right? Similarly, on this side is negative charge. So it looks like this. If this is x, right? Negative charge is on this side. I would say minus ENA here and plus E and D here. This will be the density here. This will be plus E and D, and this will be minus E and A. और this is a differential charge सही देता. This is a सोलर charge नहीं देता. तो charge सही. This is one. एक तारा देखना. दिन अभी को charge सही देंगे. Zero charge दे नहीं सकता.
Yes, sir.
Zero charge तो. No. The charge start.
Yes, sir. Mute.
Right? So we want to find the electric field from Poisson's equations. Right? D to 5 by dx squared equal to minus rho x over ES, where ES is the permittivity of the semiconductor. Right? ES is equal to permittivity of the semiconductor. Okay, we know that d5 by dx is equal to the electric field.
Sir. Yes.
So E is equal to minus gradient of the potential.
Sir.
So minus d E, the electric field by dx is equal to minus rho of x over es. Minus minus goes. Right? So to get the electric field, we have certain boundary conditions, right? Boundary condition rho doesn't convert rho of x, that is equal to minus e n a from, right, from minus xp to 0. This is, I call it minus xp here. This is n, and this is 0. Minus, I call it minus xp, the distance. I call this is xn, this distance.
Yes.
This distance is called
Yes, and
xn. And similarly, rho of x, that is equal to E and D from 0 to xn. Otherwise, the density, the charge density is 0. So I can integrate equation number 2. Integrating equation 2, right? So here as xn, so I will say d e n equal to rho of x over and dx. I would say, suppose dE on the n side, on the n boundary here, right? That is En, suppose, and 0 here.
Yes, sir.
That will be equal to, from x to xn, and E and D divided by E S and dx. That is, so here, I'll say a minus sign and minus sign here. E n equal to minus E n G divided by E s and x n minus x. That is equation number. The field. So the field is a function of x.
Sir.
Xn is a constant value, this thing. We have to h for one z. So look, the electric field is negative as we move to that side. Right? And it goes to 0 when x is equal to xn. This is why field 0.
yes, very good.
Right? Similarly,